Oh.
Is it
Oh, yeah.
something wrong?
No. Oh, yes, it is. You're right. That is very wrong. Yeah. Which page is that? Good old typo.
55.
55?
35.
All right, guys, so very quickly, there's a typo in the book. You know, it was created by humans. Example 1, page 35. So you don't have your book yet. You know ahead of time not to trust this one. Oh! Actually, it's not. I'm realizing as I read through it, I'm realizing it's not right. It's not wrong.
It's not wrong.
But it looks.
Yeah.
It's not saying. It's not. Okay, that's just evil.
No.
What's the opposite?
Yeah. I'm sorry.
What's the opposite of this? Well, what is this?
Plus.
So what's the opposite of this?
-7.
Negative 7. Yeah. That's just kind of evil. So when you first look at it, it looks like they're saying that this equals that, but saying the opposite of this is, what is it saying? This.
It's confused.
Is this. Yeah, it is this. Okay.
It's
oh my God. Yeah, okay. So they shouldn't even have said that at all. There's no need to say that. Okay, it's fine. It's fine. That's a good start. Anything else from homework or other typos or?
So it's black and white, but I honestly just don't understand. It says for problem 111, it says state the property or properties that are illustrated. What is it asking? So literally, like say.
All right, good. So let's go over the properties real quick. Okay. And to be honest, I haven't even really done any lecture in chapter 1 yet. I mean, so I'll start here, and then we'll kind of go through real quick each section and see if there's any questions. All of chapter 1 should be basically a review, but it depends on where you come from. If you're coming right out of high school, they might use a totally different book and totally different teaching style, whatever. So you got to let me know if there's something that doesn't make any sense. I live off of questions, right? That's why when I have a really quiet class, I go a little crazy. I desperately need you to say, why the hell is dividing by 0 not allowed? Stuff like that. All right, is anybody curious about that? Yeah.
So nothing makes sense.
Oh, all right. I need a little more specificity. I'm sorry. All right. I like. Oh, I have a. Oh, look at that. Spare no expense, a real eraser. Still needs work. So here's the identities. The ones we know for sure. You know, like or not the properties. We know. Do you guys know the distributive property? Mm-hmm. That's the one that we all really know. And do you know why it works? I mean, it's kind of violating order operation. So people should be up in arms about it. You're all like, this PIMDOS shit, and you spend all this time, and then you go and say, oh, you don't have to worry about it. So what is distributive property? What would this be? Well, let's put a different one there. What would that be? Well, what does order operation say you have to do? No. What does order operation say? Yeah, what's x plus 2? I don't know. Pineapple? I don't know what x plus 2 is. Right? So you can't follow order operations. So why are you allowed to do anything then if order operations is like the big rule? Has anybody ever had any problem with this? Why in the world am I allowed to do this? Have you ever thought about that? Yes?
Because there's an x.
That's why I can't do order operations, but why am I allowed to do something then?
To get them to be like terms, so you can add like terms.
There's no like terms in there, even after I distribute, right? So we know this is 3x plus 6. Still not like terms, right?
Because you want to find things, right?
It's not an equation, so I can't solve. Is that cool? It didn't have an equal sign before I did that, so let me just put this simplification. There's no equation there, right? So I can't figure out what x is. X could be anything.
Because it's the same as individually doing all the work.
All right. So watch it. I think you're on the right track. What does this mean? Don't say 3 times x. What does that mean? 3x is doing what? No, if you multiply 3x's, what do you get?
3 squared.
So exponents are just a shortcut to say how many x's you got in a row. If I had 80 x's in a row, do you want to write 80 freaking x's down? Maybe you write 79, you're like, let me double check. 1, 2. So somebody back in time, they said, math people were lazy. And we said, I don't want to do that. Let me just put a 3 up there and tell everybody it's 3x. So I don't have to write freaking 3x's or 80x's or whatever. So all the properties of exponents come off of the fact that that is not a 3. It means there are 3x's. You kind of with me?
Yeah.
So what the hell is 3x then? What's the coefficient mean was doing? What's happening with the x's? They are adding. So it's the same idea. If I collect additions of the same thing, I put a coefficient. If I collect multiplications, I can't put it in front because that already means adding, so I got to put it up somewhere else. And somebody back in time just said, let's put it up here. That sounds okay. There's nothing about this position that naturally, biologically is exponent. We created it. We could have put it underneath, but then that looks like division. Now let's put it over there. Good. All right. Are you guys kind of with me? All right, so coming back to this. If 3x means x plus x plus x, what does 3 this mean? 3 times this means 3 of these.
X plus 2, 3 times.
And what's the only operation in the whole thing? And I can add whatever order I want to. You guys know that. If I said what's 7 plus 8 plus 3, you can do 7 and 3 is 10 and 8 is 18. You can change the order. Of course you can. Because it's all addition. It's all the same level. It's all the same thing, right? So this is x and x and x is, and 2 and 2 and 2 is 6. So they said, screw that shit. Let's just do the shortcut. So distributive property is a shortcut. It's not going against the rule. You never can. I can't tell you a rule one day and then the next day break it. So if you think I did, you have to come see me because you're missing something. And that's why I think students, at some point you just go, all right, whatever, man. You just told me I can't do it and now you're doing something? Whatever. And then you just give up on math. Like, this is a bunch of shit. People made it up. They pretend like it does something for us. They keep saying, we'd be living in caves. Yeah, right, whatever. I guess...
I never thought about it that way.
Good. But that's the reality. And that's what sometimes people don't teach. Because when you know math a lot, you forget. You kind of like, well, of course that works because that's what I've been doing forever. And you forget why the hell it works. So this is the kind of question I need you to ask. Things that you thought, you're like, that's because they said it was this way. Just ask me. Please ask me. That's what I'm here for. All right, sorry. So that's distributive property. Good Lord. So we got one property. What about, does anybody remember what commutative property is? Commutative. So if I said 3 plus 6 plus 2, commutative property says that's the same thing as 3 plus 2 plus 6. So individual things, what did you guys do to get here? What do you do to go to work? You commute to work. So individuals commute. Are you with me? So what operations have this property? Addition has this property. Does multiplication? Yeah. So 3 times 6 times 2 is, of course, the same thing as 3 times 2 times 6 is the same thing as 6 times 3 times 2. You can rearrange them. So commutative property is all about rearranging. Does subtraction have this property? Hell no. 7 minus 2 is not the same as 2 minus 7. Division doesn't have this property. 8 divided by 4 is not the same thing as 4 divided by 8. So it's only addition and multiplication that have this property. Cool. I like it. You guys with me so far?
Yeah.
Good. All right. And then there's another one that's sort of like this, but it's called associative property. Somebody remember what that one's all about? Has anyone ever heard about that one? Yes? You guys like, yeah? Yes? All right, I can do that.
I mean, I'm looking at the book.
Uh-oh.
Where the parentheses.
Yeah. So all it says is I can regroup it like this. Those are the same thing, right? But you see the difference between this and this. I could throw parentheses in here too, and it would still be commutative. Because what moved here? What moved here? Did any number move? No. What moved?
Parentheses.
The parentheses got to move. So parentheses associate. Okay, associate. Oh, I'm going to go over here and associate. I'm going to mingle. Whatever. All right. Silly example, but it's going to stick in your head, hopefully. So parentheses associate. Individuals like us commute. So when an individual thing moves, that's commutative. When parentheses get to move, that's associative. So the same properties have this, same operations division and subtraction do not have this property. Right? If you don't believe it, what is 6 minus 2 minus 7? How do you do that?
4,
Good. 4 minus 7 is?
3.
Negative 3. If I move the parentheses and do this, 6 minus 2 minus 7, what's that? 6 minus negative 5. 6 plus 5, right? Negative, negative is plus. 6 plus 5, 11. Are those the same?
No.
No. So subtraction, division, they do not have associative or commutative property. All right, I like it. So on one level, I almost don't care too much about the words that we use. You have to be able to do it in the right time. You with me? You just have to be able to use them. But there are going to be some times where I ask you, identify the property. So you do have to know what the words mean, right?
I hate the words in math. I like the numbers. Show me the numbers.
I got you. So I put a lot more emphasis on being able to do this stuff, but there will be some times I'm going to ask you the property.
Yeah.
All right, so if you can't do this, you'll pick up most of the points on the numbers. Yeah. So don't worry too much. But do try to figure out what the words mean. There are a couple more, I keep saying the word, properties. Everybody cool with this?
Yes.
All right. There's something called the identity property.
Mm-hmm.
There's identities of addition. And really, if you think about it, additive identity. What do you add to something to keep it the same so you don't change its identity? 0. So 0 is the additive identity. It's the thing you add to something that keeps its identity. If you add 1 to something, you've changed it, right? I'm now 9. So it's 0 is the additive identity. What's the multiplicative identity?
1.
Yeah, what do you multiply by to keep it the same? 1. So 1 is the multiplicative identity. I like it. So I know it sounds like we're making it, 0 and 1, you're calling and making all these crazy words about them, but they become important the further you get along in math. You can have entire systems of math that don't have a multiplicative identity, for example, or something. But that's like way further. Way further. What about inverses? What the hell does inverse mean?
Like the opposite.
Opposite. I love it. So the additive inverse of something, what's the additive inverse of 4? Negative 4, because when you add them together, they cancel. They become the identity again, right? So 4 plus negative 4 is 0. So what's the additive identity of A?
Minus A.
Negative A. That's all, right? Whatever A is, the additive identity would be negative is.
Inverse?
Say again?
The additive inverse.
Additive inverse, exactly.
Not the identity.
Oh, I keep saying identity. I'm sorry. Thank you. I'm so stuck on identity there for some reason. It's a really cool movie with John Cusack, right? Have you ever seen it? A and negative A. What's the multiplicative inverse? What do you multiply something by to cancel it out? So if I had, so the multiplicative inverse, if I had 4, what do you multiply by to make it cancel?
0.
No.
Negative.
How do you cancel?
1 over 4.
Beautiful. Because what's the multiplicative identity? 1. So really, the inverses are whatever makes it become the identity. And that's the effectively canceling it out.
Got it.
So to cancel 4, I multiply
Yeah.
by 1/4. So they cancel, right? All right, let me stop there for a second.
It's technically
So it is?
4 over 1.
So, yeah, exactly. It's 4 over 1. So what's the multiplicative inverse of 2/3?
3 over 2.
3 over 2. So it's also known as the reciprocal, right? Because these will cancel, bam, bam. Good. So what's the multiplicative inverse of A?
1 over A.
1 over A. So what's the only number that does not have a multiplicative inverse? 0. I like it. All right, let me stop there for a second. We'll talk about 0 here in a second. Is everybody decently cool with the properties? And they're all in the first chapter, so you can review them in there. You've all heard these before, but maybe not exactly this terminology, possibly. Depends. Okay. Does everybody know why you can't divide by 0?
Because it gives you like an algebra inverse or something like
Not quite. There are not real numbers.
that. Yeah, it's like
They exist.
you can't multiply by infinity times infinity, right?
You sort of can.
What else? I remember there's like 7 of them.
You ready? It's crazy. What do you call it when you have this? What do you call it? What's the word you use?
Undefined.
Undefined. So, did anybody ever tell you why we say that? So watch this. You ready? Why is 6 divided by 2 3? Don't say because 2 goes into 6 3 times. Say, be a little more precise. Why is 6 divided by 2 equal to 3? Because 2
Multiplies by 3.
times 3 is 6. So 3 is the number that is defined such that when you multiply it by 2, you get 6. Holy shit, that's a very complicated way to say that, right? I'm not going to do that all the semester, don't worry. 4, when you add it to 2, what you get, no, it's good. But watch this. 6 divided by 0 would have to be the number defined such that when you multiply by 0, you get 6. Is there any number defined to do that?
No.
So we call it freaking undefined. Do you see what I'm saying? So these are the kind of things that I don't think anybody ever tells you. They say it's called undefined, just remember that, write it down. Yeah. But you should be like, why is it called undefined? If they can't answer you, they should go look it up, figure it out. All right, maybe. Is that cool? All right, I like it. So that's why we call it undefined. There is no number I can put there that would multiply by 0 to make 6, so there's no number defined to do that. Cool. Is there any other specific questions from chapter 1? All right. So I think what I want to do is, we have number 3 on the warm-ups page still to do, right? I think we finished number 2 on the warm-ups page. I have copies of an answer key for you.
Yeah.
Hopefully I brought it with me. Yay, Jeff. I'll give that to you here in a minute. What I think I want to do first is to quickly run through chapter 1. I'm going to do remarkably quickly. You must slow me down if I hit a weird point. You understand? If you're not somebody who likes to speak up, you need to work against that. Now, I'm not going to go this fast for the whole semester, so don't freak out. All right. But chapter 1 is review. I know we all hate fractions.
We literally started like in the...
We're going. This is why we're going very, very quickly.
Oh.
Let me see where I want to start. What's the difference between a prime number and the other thing? What do you call the other thing?
Composite.
Composite. I like it because it's composed of more than one thing, right? So what's the difference there? Give me an example of a prime number.
A prime number has factors. Composite number, don't have any number, any factors.
Prime, composite has something, right? So, what kind of number is 17?
Prime.
Why?
Because no factors for 17 we
Good.
can, only
Except for what? What's the only way to break it up?
Yeah.
1 times 17, the most, the simplest way. It's the only way to do it. So it's a prime number, and a composite number would be something like 18.
Yeah.
Because that would be 2 times 9.
6, 9, yeah.
Oh yeah, I got you. So 6 and 3, and so forth, yeah. I like it. So 2, 3, 3. When you do this kind of thing, prime factor tree, I call this the DNA of the number. Because if you put those back together, you only get 18. It's like if you put DNA together in a certain way, you only get a frog, or you only get, right? So that's the DNA of 18. Right?
Okay.
Yeah, okay, whatever you want to do, Jeff. Sure. All right. All right, so that's simple. What do we call the number 1, though? This is weird. 1 itself is not prime or composite. We just call it the unit. Right? I don't know. It sounds like it's a wrestler or something. Here it comes, the unit. I don't know. It's just me. All right. So that we just call it unit. Right? Okay, sounds like a cyborg. I am unit. I'm Groot. I am Groot. All right. Fractions. I know we all hate fractions, but we talked a little bit about fractions yesterday. We didn't talk about stuff like how do you change this into a mixed number?
How many? 4 and 13?
So
3 and 1 over 4.
1 3 over 4.
Yeah, so it's just like long division. But let me show you a slightly different way, real quick. I don't mean to do this to confuse you, but just watch. It's kind of neat.
Your page, what page are you on?
Sort of page 20, 21, sure. I don't know, wherever they talk about mixed numbers. Sorry. I'm talking about the ideas. I have no idea where in the book it is exactly. Sorry. I'm in chapter 1, which is everything you're supposed to know already. 4 does not go into 13, so that's why there's a problem. But 4 does go into what number that's below 13?
12.
Where's the closest empty seat for Oh, there's one here? Yeah. Can you make your way? We had interesting class organizational trouble earlier. So watch this. Isn't 13 12 plus 1?
Yes.
And what's being divided by 4?
3.
12 and 1.
Oh,
So 12 over 4 plus 1 over 4. What's 12 divided by 4? 3 and 1/4. Right? This is important because when we start talking about radicals, somehow it relates to this. Because I do the part I can do, and I leave the part that I can't do. So somehow that's going to relate to radicals, but we're not there yet. Don't freak out. All right, cool. I'm not saying you have to do it this way from now on. I'm just saying that's another way to look at it. All right. And of course, to change it back is simple. If I had 7 2/3, how do you change it back into improper mode?
Just multiply at the time.
Yeah, and now you see why. This really means 7 plus 2/3. Is that cool? What I hate is when people think that says 7 times 2/3. So this notation is kind of evil.
Wait.
If they meant 7 times 2/3, they have to put that in parentheses or something, right?
Mm-hmm.
Yes, ma'am.
Okay, I'll just let you finish and then I'll tell you if I have a question or not.
All right. Okay, that's the way it's going to work. Can you add those? No, it has a 1. That will always have a 1 underneath it, won't it? So that will always need this. So you would have to multiply by 3. That's why you multiply by 3, because you would. And then you add this, because that would be the next thing you would do, right? That's why the shortcut works. And again, I just want to make sure you know why things work. Because the more you understand why things work, the firmer that foundation is to build on. It's when you just learn, like, okay, I just memorized how that works, and then you got shaky shit down here. It's hard to build on that. Yes?
Say that again.
Okay. So I know everybody knows the shortcut. But what this really says, just like this really means this. When you write that, it means this. We just don't write the plus sign just to save time. Let me stop there. Is that cool, everybody? I see some of you guys are bored. It's cool. Just sit there. Bored is good. That means you understand it. Just be bored for a while. Isn't this 7 over 1, right?
Yeah.
So what does this need? To make it the
To
same
make it the same, yeah.
This needs a 3. No matter what that number is, isn't that going to need it? Because it's over 1. If I would have put a 5 down there, he would have needed a 5. So I really want you to see why this shortcut works. 3 times 7, why do we do whatever's down there and multiply with this? Because that's always what this guy's going to need. Do you see that? And then, so once I give it a 3, the next thing I would do is I would add 21 and 2. And that's what we do next. We say 21 plus 2. So it's important for you to know why shortcuts work. I don't like to use a lot of mnemonic devices. You guys know what mnemonic device?
Are you calculating?
Like, no. Mnemonic device like My Very Educated Mother. Does anybody know what that is? My Very Educated Mother? Mars, Mercury, Venus, Earth, Mars, so forth. Right? Of course, Pluto is gone. Sorry, Pluto. We got a new ninth planet. They're trying to find. Yeah, do you guys know that? They found evidence. They haven't seen it yet, but they know by observing how things are moving around way the hell far away from us. There's a gas planet that's our 9th planet, and Pluto's like, man,
I thought they were going to have like a convention to see if Pluto would be a planet again.
no, it's been decided. Sorry.
Really?
It's a dwarf planet. Say it. Yeah. So that's the thought now. Yeah. So, but anyway, they did discover a new 9th planet, way the hell out. It takes 10 to 20,000 years for this planet to go around the sun. It's that far away. It's very, very far away. Sorry. Anyway, that's all aside.
So is that it? That's the end of the problem? Or
Oh, sorry. So of course it would be that. Cool. All right. Oh, what was I about to do? I forgot. So we already talked about order operations. I explained why it's a little evil that we just do PEMDAS in a straight line. Some teachers actually teach multiplication as first, and those teachers need to be disciplined or fired. Something has to happen. So I'm sorry if that happened to you in the past. I'm here to clear that up. Blah, 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 blah. Oh, we already know that. We already know those. Very quick word about, I don't want to spend a lot of time on this, but what do you call these kind of numbers? Somebody know?
Natural number? No.
Yes, I like it. Natural numbers, positive integers, but these are the natural numbers. Now, if I add in there, now, did you guys know that the Babylonians,
No.
the Babylonians,
No.
everybody understand
Yeah.
Babylonians?
Babel, yeah.
Their civilization didn't know what zero was. They hadn't invented the idea of zero until right before the civilization fell. They went, oh, I know what zero is. What? We're done? Okay. So I teach a class, Math 120, and actually teach Babylonian number system and show you the symbols they used. Because the symbols we use, they didn't have to be this way. People just said, that. Yeah, let's use that for 2. Sure. Fine. You guys kind of...
Yeah.
So when you came up with the idea of zero, that had to be invented, the idea of zero. We call this, now it's funny because a zero looks like a hole, so we call these whole numbers. Right? So I always have this little thing about, back in the day, a caveman had a rock, he's happy. He loses his rock, now he's got 0 rocks, oh shit. So then, of course, what does he have to do? He needs that rock so he can crush stuff, right? So he has to borrow a rock. Right? So when you borrow, you are in debt. So you have to introduce the idea of negative numbers, right? So when you introduce the idea of negative numbers, what do we call that now?
Integris.
Integers.
Again, sorry.
Integers.
Integers.
Yes.
Sorry.
Right, we have to Americanize words like croissant, we call it croissant.
You will love this semester too much money.
So these are what came naturally to us, 1 finger, 2 finger. We can see that. The idea of zero, you guys are like, of course there's zero, but it had to be invented. You're lucky you existed after it was invented. And then these had to be invented. And for the longest time, actually, really high-up mathematicians didn't believe in negative numbers. They're like, how could there be negative numbers? It doesn't make any sense. Which kind of led to the unfortunate naming of imaginary numbers. Have you guys ever heard of imaginary numbers? And it's just a bad name. It's just because there were mathematicians who didn't believe they existed and the name stuck. So a lot of students take that to mean, I knew you were making all this shit up. Now you're finally being honest. Imaginary freaking numbers. Say again? Well, that's not imaginary, it's just freaky. It's just a really large number. It's what the name Google's based on. Googleplex is like 1 followed by 100 zeros. Yeah, but it's just a name for a very big number. What I'm talking about is square root of -1. But don't worry about it. That's later. And then so he borrows a rock, so he's in debt. And then he drops his rock, so the rock breaks in half. So he has to invent the idea of fractions. What do we call those kind of numbers? Fractional numbers. Rational. I love it. Because the root word is ratio. So rational numbers are fractions. 7/4. What about 3? Is that a rational number?
Yes.
Hell yes, 3/1. So anything that be written in the form of a whole number, the ratio of 2 integers. If they can be written like that, it's a rational number. So what are irrational numbers?
Negative.
No, those are fine. -4/7, that's totally rational. Pi, good. Pi is irrational. 3.1415, nice, blah, 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 blah. That's as far as I want to remember. I don't have a lot of brain cells left.
Root of 2.
Yeah, good. Square root of 2.
5.
Square root of 5. Yeah, any square root I can't do. I like it. All right, how are you doing? Yes?
Negative numbers?
Negatives are fine. And it's funny because that's a lot of mathematicians back in the day, they would have called those irrational. They would have said those don't exist, but now we know they completely exist.
What is that what does that say?
Where?
The top.
No.
Natural numbers?
Okay, natural.
Yeah, sorry. Yeah, the day that I can't read my own writing is when I retire, but yeah, yes.
So then where do decimals fall?
Good, I like beautiful. Oh, you're like my segue person. So if I said 1.2, why does that go there? Because what's 0.2 as a fraction?
1/10.
5/10.
Yeah, 2/10, which is 1/5. I like it. You got to be careful. 1/2 would be what? 0.5. I like it. Cool. You guys with me? So any decimal that stops, I don't care how long it takes it to stop. If it does stop, I can put it over 1 followed by a lot of zeros, right? So for example, this is 1 2/10. 1 1/5. So what about 0.79278? What place is that in? What place is that in?
Between 0 and 1.
No. Like this is in the tenths place. What place is that in? Tenths, hundredths, thousands, 10,000s, 100,000. So you say 79278 divided by 100,000. How many numbers are here? 1, 2, 3, 4, 5. How many zeros did I put? 1, 2, 3, 4, 5. Yeah. So if the decimal stops in the 87th place, you could put it over 1 followed by 87 zeros. So it would be fraction, right? It would be rational. So the only kind of decimals that don't fall here are the ones that don't stop and have no pattern to them. Because do you guys know what 1/3 is as a decimal? What's 1/3 as a decimal? See, if it has a pattern to it, 0.33333, if it repeats itself somehow, it's going to become a fraction. These don't stop and they don't have a pattern. That we know. If people keep trying to get pi to go further, like, please have a pattern, pi. No, I don't think it does. Do you guys know where pi came from? Yeah, but where did pi come from? Anybody know? Yes, exactly. Very quickly, I'm sorry. Any circle you draw, I don't care how small or how big, if you take its circumference, that's all the way around, right? Divided by its diameter, you always get the same number. So that's where the circumference formula came from. I don't know if you guys remember. That came after this. So it's freaked civilizations out. The Egyptians had their own estimation for what pi was. The Greeks had their own estimation for what pi was. All these civilizations. And then we have computers spitting them out at us, right? They can calculate pi out to the 5 billionth place now. It's crazy. You guys semi with me? Yes. At least everybody's looking this direction. All right. All right. Sorry. I do sometimes go off on tangents, but I go off on a lot of tangents in chapter 1 just because there's a lot of stuff in here. Right? So don't be too worried about how I'm going to teach you. I'm going to spend a lot of time on adding, subtracting numbers. You should all be able to do 7 minus 10, right? Right? If you have any trouble with that, I always talk about money. If I got $7 and I owe you 10, can I pay you off all the way? I'm still going to owe you. So if the negative one's bigger, the end result's going to be negative. So forth. I'm not going to spend a lot of time on that. I'm going to hope you know how to do that. Same thing with multiplication and division. 1.7 is a property, so we already did that. I'm flying through here, by the way. And then 1.8 is like terms. So let me talk about like terms just for a minute. And you're like, it's not up to me, man. Just do it. Try this here. Well, actually, what do you guys think? If I ask you to simplify this, what would you say?
Combine like terms.
So that's what you would do. If I ask you to do that to this, beautiful. It's already simplified. Because are there any... So to be like terms, you have to have the same variables, and the same amount of each variable. So nobody in there has 1x, nobody else in there has 1y, nobody else in there has xy, nobody else has y squared. So there's no like terms. All right, maybe. So what about this here? All right, so good. So the negative 3b squared, negative 7b squared makes negative 10b squared. So what about these?
6AB.
How many a's does this have? How many b's? How many a's does this have? How many b's? They're like terms. I just wrote this out of order, that's all. What is the operation here?
Multiplication.
Do I have to multiply a certain
Yes.
order? I can multiply any order I want to. So isn't this 2ab? I know this seems like a trick, but when you're working stuff out and distributing, you might write something out of alphabetical order. You got to realize it's still like terms possibly with something else. So it's not a trick, it just might happen, right? So you just got to realize this is 2ab. So then how many ab's do I have?
6ab.
6ab. And that's where you stop. You can't put those together. Because I got 6 of these minus 10 of those. I can't put those together. So I got negative 4. No, you can't consolidate that any further. All right, cool. How we doing?
We're good.
We're good. Okay. Spokesperson. All right. So that's all I got to say about that. Good. So now let's get into the meat of today. So now I'll slow down a little bit. I want to get into chapter 2. Chapter 2 is all about solving equations. I am sort of going to not be able to stop myself from assuming you know how to solve some equations, right? But I'm going to start sort of as if you don't know. I'm going to go a little bit quickly at first. And the reason that solving equations is so important is because when we make observations, to predict the weather, which isn't really done well, is it? But it's not our fault. There's just too many variables. The whole idea of the butterfly flapping its wings is actually not far from the truth. So many variables affect each other that it's almost impossible. But we do our best. So we make observations and we create equations that we plug observations into. But then if we want to predict something, we have to use algebra to predict what's going to happen, right? We have to solve for this x or solve for that y or whatever. You guys kind of with me here? Or if I'm a company, I'm going to create an equation for my profit. And where am I going to try to get myself? I'm going to try to get myself to be there, right? So then I got to figure out, well, what does that mean about how many things I got to make and how many things I got to sell? So I got to solve the equation to figure out how to get there. Maybe. So solving an equation is like the bread and butter of any damn thing you want to do, to be honest. Now, could you live life and never solve an equation? Of course you could, right? Could your life be a little better if you knew how to solve an equation? Of course it could, right? But anyway, I'm not going to defend math too much. So, for example, let's do this a little bit sideways from what you're used to. If I start with, somebody give me a value for x. What do you want x to be?
3.
7 is the first thing I heard. 2 back 3. I'm sorry. I heard 7. So normally I don't know what x is to begin with. So I'm going to kind of do this a little backwards. So if x is 7, what is x plus 4?
7 plus 4.
So what's x plus 4?
11.
All right. Is everybody cool with that? All right. So then what is... I should... So if I want to solve this equation, I'm going to undo what somebody did to x. That's why I'm always trying to get x by itself. That's why you almost always do the opposite operation that you see, because you're trying to pull away the layers and get x by itself. So you see what the hell it was. So if I subtract 4, I'll figure out what x was. That's what algebra really does for us. But you could just look at this equation and solve it. If you didn't know this, you know how to... what do you add 4 to get 11? 7. And you're like, I don't need algebra. See? But algebra, of course, helps when there's a lot more shit going on. You can't do it in your head, right? What if we do something else? If I start with x equals, I'll use 2. So what's 3x?
3 by 2? 6.
6. So what's 3x minus 2?
4.
You guys with me so far?
Yep.
So 3 times that is 6, and then 3x is 6. So what's 3x minus 2? It must be 4. Mm-hmm. So what's 3x minus 2 plus 5x? So you guys can do that. What's 3x minus 2?
4.
And what's 5x?
9.
6.
10.
10. All right, let me make sure you guys are with me. You guys see that?
Yeah.
3x minus 2 is 4.
Okay.
5x is 10. What's 4 plus 10? 14. Now, if I give you this equation, and I said solve for x, this is not as easy to do in your head, is it? You can't just do that in your head. So what algebra does for us is it collects things and makes it simpler and simpler and simpler. That's its. So if it can get to this point, then I almost don't need to do this step. I know 7 and 4 is 11, so I know the answer is 7. But when I'm at this step, I'm like, I don't know what the freaking hell's going on here. Shit. So the algebra steps in and says, let me make this look better for you. Let me make this look better for you. All right, so what would be the first thing I would do here?
Add 2 to both sides.
Oh, cool. I like it. Add 2 to both sides. And combine like terms. Is that cool?
Yeah.
You stop there. Is that decent? And then, sorry? Yeah. So far is it good. Sorry, I'm not done. I like that. She's like, dude, man. I like that. Keep me honest. So what's the last thing to do? Divide by 8. So you get x is 2, which we started with it, right? Now in real life you don't start with the answer. But if I wanted to make a problem for you to solve and I want the answer to be 2, I can just do it like this. I don't normally do that, but if I wanted to. Alright, maybe. So you're trying to undo what somebody theoretically did to x, to figure out what x was. That's what you're doing when you're solving equations. So let me, I'll tell you what, let me do this. Oh, I forgot, I totally, well no, we'll do this right in a minute. Because number 3 on that warm-ups is going to lead into the dreaded word problems, right? So I'm going to hold off on that for just a minute. Let me shut the hell up for just a few minutes. I got a little handout that's got the steps for solving equations in general. So I want to let you guys work just to see where everybody kind of is with solving equations. You can work in groups. It's obviously very easy to get together in groups. Yes? Oh, yeah, sure. Anybody else need that warm-up sheet while I'm thinking about it? If I have any more? Scheiße. Anybody else need that warm-up sheet? Do I have more? Yes. No. Yeah, sure. Okay. Here. Are you going to come back? Okay. Here's, I'm going to give this. Oh, you got it. Good. Oh, and this here too. So. Okay. All right, guys. So let me give this to you.